Right now, as you listen to this, humanity stands at a threshold we've never truly confronted. We've sent machines beyond the planets, we've photographed the edge of the observable universe, we've mapped galaxies billions of light years away. And yet, despite all of this, despite every technological leap, every mission milestone, every bold declaration about becoming an interstellar species, there is a countdown ticking that most people don't know exists. A countdown that determines whether any human being will ever leave the solar system alive. Not in 1,000 years, not in 10,000, not ever. This isn't about technology we haven't invented yet. It's not about political will or funding or international cooperation. Those are all solvable problems. The countdowns we're talking about are written into the physics of space itself, into the biology of the human body, into the mathematics of distance and time and energy. And every single one of them ends the same way, with the boundary of the solar system remaining forever out of reach for living, breathing human beings. The clock is already running. And to understand why no human will ever escape, we need to start with the most fundamental countdown of all, the one that begins the moment a spacecraft leaves Earth's orbit. Let's say it's the year 2045. After decades of preparation, the first crewed interstellar mission launches from Earth. The destination, Proxima Centauri, the closest star system to our own, just over 4 light years away. The spacecraft is unlike anything humanity has ever built. Nuclear-powered, equipped with life support systems designed to function for decades, carrying a crew of 6 in rotating shifts of hibernation and activity. The mission timeline is ambitious but theoretically possible. A 70-year journey to reach the Proxima system, study it briefly, and send data back to Earth. 70 years. That's the countdown everyone focuses on. That's the number in the press releases, in the mission patches, in the documentary voiceovers. 70 years to cover 4 light years of distance. It sounds achievable. It sounds like something humanity could survive. But there's another countdown that starts the moment the engines fire. A countdown measured not in years, but in the gradual breakdown of every biological system that keeps a human being alive. And this countdown doesn't care about mission timelines or human ambition. It simply runs out. The human body was not designed for deep space. It was shaped by millions of years of evolution on a planet with a protective magnetic field, a thick atmosphere, and a gravitational pull of exactly 1 g. Every cell in your body, every chemical process that keeps you conscious, every structural element from your bones to your brain, all of it is calibrated for Earth. Leave that environment, and the countdown to systemic failure begins immediately. First, the radiation. Earth's magnetosphere shields us from the constant bombardment of cosmic rays and solar wind, high-energy particles that stream through space at near-light speeds. On Earth's surface, you receive about 3 millisieverts of radiation per year from natural sources. On the International Space Station, orbiting within Earth's protective bubble, astronauts receive about 144 millisieverts per year, roughly 48 times the surface dose. But beyond the magnetosphere, in the open void between planets, the radiation environment becomes incomprehensibly hostile. A spacecraft traveling to Proxima Centauri would pass through interstellar space where cosmic rays strike unimpeded. The dose rate climbs to approximately 600 millisieverts per year. Over a 70-year journey, a crew member would accumulate 42,000 millisieverts, 42 full sieverts of radiation. For context, A dose of 5 sieverts delivered over a short period is fatal to half of all humans exposed. Spread that over 70 years, and it doesn't kill you immediately. Instead, it degrades you slowly. The countdown manifests in DNA. Cosmic rays are not like the radiation from a medical X-ray machine. They're high-mass atomic nuclei moving at relativistic speeds, and when they strike a cell, they don't just damage it, they shred it. A single heavy ion can tear through 50 cells in a row, leaving a trail of broken DNA, ruptured membranes, and triggered mutations. Your body can repair some of this damage, but not all of it, not even close. Over years, the errors accumulate. Cancer risk doesn't just increase, it becomes nearly certain. Cataracts cloud your vision. Your cardiovascular system weakens as radiation damages the endothelial cells lining your blood vessels. Your central nervous system begins to misfire as neurons die and aren't replaced. Studies on astronauts who spent just 6 months on the ISS show measurable cognitive decline, memory issues, and motor control degradation. Now extend that to 70 years in an environment 50 times more radioactive. By year 10 of the journey, the first crew member develops leukemia. By year 20, half the crew is dealing with tumors. By year 30, the cognitive impairment is severe enough that mission-critical decisions become unreliable. And this is assuming perfect health at launch. No underlying conditions, no genetic predispositions, no bad luck. You could shield the spacecraft. You could surround the crew compartment with water tanks, polyethylene, or even lunar regolith. But here's the problem. Effective radiation shielding for a 70-year mission would require so much mass that the spacecraft becomes unliftable. NASA's calculations suggest you'd need at least 20 centimeters of water-equivalent shielding in all directions to reduce cosmic ray exposure to survivable levels. For a crew compartment large enough for 6 people to live in for decades, that's hundreds of tons of shielding mass. And every kilogram you add is a kilogram. The engines have to accelerate to interstellar speeds. There's a countdown within the countdown here. The more shielding you add, the heavier the spacecraft. The heavier the spacecraft, the more fuel you need. The more fuel you need, the heavier the spacecraft. It's an exponential trap. Run the numbers, and you find that a fully shielded crewed interstellar spacecraft would require so much propellant that it becomes physically impossible to launch with any technology we currently possess or can foresee developing. So, the radiation countdown ticks on. Unshielded or undershielded, the crew's biology degrades year by year, and there's no way to stop it. But radiation is just the first countdown. Simultaneously, a second clock is running, one governed by the absence of gravity. In zero gravity, the human body begins to disassemble itself. Without the constant load-bearing stress of standing, walking, and moving under Earth's gravity, your bones interpret the lack of force as a signal that they're no longer needed. Osteoclasts, cells that break down bone tissue, begin to outpace osteoblasts, the cells that build it. You lose approximately 1 to 2% of bone density per month in weightlessness. After 6 months on the ISS, astronauts lose about 10%. After a year, 15 to 20%. Now project that forward. After 5 years in zero gravity, you've lost half your bone mass. After 10 years, your skeleton is so brittle that a minor stumble could shatter your femur. After 20 years, your bones resemble those of a severe osteoporosis patient in their 90s, porous, fragile, structurally unsound. And unlike muscle, which can be partially preserved through rigorous exercise, bone loss in microgravity is relentless. You can slow it with resistance training and pharmaceuticals, but you cannot stop it. The countdown extends to your muscles. In zero gravity, your heart doesn't have to work as hard to pump blood. There's no gravity pulling it down into your legs. So your heart atrophies. Your leg muscles, no longer needed to support your weight, shrink. Studies show astronauts lose up to 20% of muscle mass in just 11 days. Over 70 years, even with the most aggressive exercise regimens, your muscular system would degrade to the point where returning to a gravity environment, even one as weak as Mars, would be physiologically catastrophic. Then there's the fluid shift. On Earth, gravity keeps your bodily fluids distributed. Blood pools in your legs, cerebrospinal fluid stays where it belongs. Your organs sit in their proper positions. In zero gravity, fluids migrate upward. Blood rushes to your head. Your face swells. The pressure inside your skull increases, compressing your optic nerves and causing vision degradation, a condition astronauts call visual impairment intracranial pressure syndrome, or VIP. Over months, this can cause permanent structural changes to the eye. Over decades, it could lead to blindness. Your immune system weakens. Your balance, governed by the vestibular system in your inner ear, which relies on gravity to function, stops working correctly. When astronauts return from 6-month ISS missions, they can't stand without assistance. They stumble. Their spatial orientation is scrambled. Extend that to 70 years, and the question isn't whether they could walk on a planet again. It's whether their neurological systems would even recognize gravity as a concept. Every system in your body is on a countdown to failure in microgravity. And unlike radiation, where you could theoretically add shielding, gravity is not something you can add to a spacecraft. You could spin the ship to create artificial gravity through centrifugal force, but that introduces a cascade of engineering problems: structural stress, navigation complexity, power requirements, and again, mass. A rotating habitat large enough to produce Earth-like gravity without causing debilitating Coriolis effects would be enormous, and heavy, and expensive, and not something we know how to build at interstellar scales. So the bone loss continues, the muscle atrophy continues, the fluid shift continues, and the crew that launched healthy and strong becomes, year by year, less capable of surviving in any environment other than the weightless void of their ship. Now, layer in a third countdown, the psychological one. Imagine you are sealed inside a container roughly the size of a small house. You share this space with 5 other people. You will never leave it. You will never see a horizon. You will never feel wind or rain. You will never see a new face or hear a new voice that isn't transmitted across light years of delay. The walls around you are all you will know for the rest of your life. The first year, it's an adventure. The second year, it's routine. By the 5th year, the monotony is crushing. By the 10th year, the sensory deprivation has measurable neurological effects. Human beings are not designed for extreme isolation and confinement. Our brains require novelty, social complexity, environmental variety. Remove those, and the mind begins to break down. Studies of Antarctic research stations, the closest analogue we have to deep space isolation, show that even with regular supply drops, internet access, and the knowledge that rescue is possible, crew members develop depression, anxiety, cognitive impairment, and interpersonal conflict. Now remove all of those safety valves, no resupply, no internet, no rescue. Just 6 people in a can, drifting through the void with 70 years ahead of them. The statistics are grim. On submarines, on remote research stations, in sensory deprivation experiments, the pattern is consistent. Humans crack. The timeline varies by individual, but the outcome doesn't. Some withdraw into catatonia. Some become paranoid or aggressive. Some lose the ability to distinguish reality from hallucination. And in an environment where a single person's breakdown can jeopardize the entire mission, where there are no doctors, no therapists, no intervention teams, the psychological countdown becomes a mission-critical failure point. Then there's the social countdown. 6 people, together, for 70 years. No escape, no privacy beyond a thin curtain. Every annoyance, every quirk, every personal habit amplified by decades of repetition. Friendships curdle, romances turn toxic, grudges calcify. The research on small isolated groups is unequivocal. Cohesion decays over time, especially when there's no external relief, no rotation of personnel, no break in the routine. By year 20, the crew barely speaks to each other. By year 30, there are factions. By year 40, open hostility. By year 50, someone has snapped. Maybe it's violence, maybe it's sabotage, maybe it's just a quiet refusal to continue performing essential tasks. It doesn't matter. The outcome is the same. The mission fails not because of engineering, but because the humans inside couldn't endure the countdown. And here's the cruelest part. Even if you solved every single one of these countdowns, even if you invented perfect radiation shielding, artificial gravity, and psychological conditioning that somehow made 70 years of confinement bearable, you would still face the countdown embedded in the journey itself. The simple, inescapable fact that you cannot go faster than the laws of physics allow. Proxima Centauri is 4.24 light-years away. That's the closest star system. The next closest, Barnard's star, is 6 light-years. Then Lumen 16 at 6.5 light-years. Then Wolf 359. Then Lalande, 21,185. The distances scale exponentially, and at every tier, the timeline stretches further. Let's say you build a spacecraft capable of traveling at 10% the speed of light, an achievement that would require technology we don't currently possess and energy reserves we don't know how to generate. At that speed, reaching Proxima Centauri would take 42 years, not 70, 42. A human lifespan, barely. But here's the countdown problem. 10% light speed is 30,000 kilometers per second. For reference, the fastest human-made object ever built, the Parker Solar Probe, reaches a top speed of 191 kilometers per second. That's 0.064% the speed of light. To reach 10%, you'd need to go 157 times faster. The energy required scales with the square of velocity. You're not talking about incremental improvements. You're talking about energy expenditures on the scale of small stars. Even if you had that energy, you'd face the fuel problem. Every kilogram of propellant you carry is a kilogram you have to accelerate. The rocket equation governs this mercilessly. The faster you want to go, the more fuel you need, but the more fuel you carry, the heavier you are. So you need even more fuel, which makes you even heavier. It's an exponential trap with no escape. The numbers don't work. They never have. They never will. Okay, you say. So we don't use chemical rockets. We use nuclear propulsion. Ion drives, fusion engines, antimatter. Sure. Let's grant that. Let's assume you build a fusion engine capable of sustained burns over decades, something we're centuries away from even prototyping. You still face the countdown of acceleration. To reach 10% light speed, you have to accelerate, And if you want the crew to survive, that acceleration can't exceed a few Gs, and even that is punishing over extended periods. A sustained 1 G acceleration, equivalent to Earth's gravity, would get you to 10% light speed in about a year. But here's the problem. You have to carry enough fuel to accelerate for a year, then carry even more fuel to decelerate at the destination so you don't just fly past at relativistic speeds. The fuel mass required becomes absurd, thousands of times the mass of the payload. Run the numbers with the best theoretical propulsion systems we can imagine, and the countdown remains the same. Decades to reach even the nearest stars, and that's assuming perfect technology, unlimited budgets, and zero failures. And we haven't even talked about navigation. Space is not empty. At 10% light speed, even a grain of sand becomes a kinetic weapon. A single particle of dust, smaller than the width of a human hair, carries enough energy at that velocity to punch through metal. A pebble would vaporize the spacecraft. You can't see these objects coming. There's no radar system capable of detecting millimeter-scale debris at interstellar distances with enough warning time to maneuver. You'd be flying blind through a cosmic minefield, and the countdown to collision would be random, invisible, and catastrophic. Then there's cosmic dust. Interstellar space isn't a perfect vacuum, it's filled with hydrogen atoms, about 1 per cubic centimeter. At normal spacecraft speeds, that's irrelevant. At 10% light speed, those hydrogen atoms hit your hull with the force of radiation. Over years, the cumulative damage erodes your shielding, degrades your instruments, and introduces yet another countdown to structural failure. Every single aspect of an interstellar journey is governed by countdowns, stacked on top of countdowns, each one ticking toward a different failure mode, and all of them running simultaneously with no way to stop the clocks. So when people say, "We'll send humans to the stars someday," what they're really saying is, we'll ignore every countdown that makes this physically, biologically, and psychologically impossible. But maybe, you think, maybe we don't send humans awake. Maybe we freeze them. Maybe we put them in cryogenic suspension, stop the biological countdowns, and wake them up when they arrive. It's a staple of science fiction. It sounds plausible. Except we don't know how to do it. We can freeze individual cells. We can freeze embryos. We can freeze small tissue samples. But a whole human body, a living, functioning organism with trillions of cells, all of which contain water, all of which will form ice crystals that rupture cell membranes and shred tissue at the molecular level. We have no idea how to prevent that. Every attempt to freeze and revive a mammal larger than a hamster has failed. The countdown to tissue death begins the moment freezing starts, and we have no way to reverse it. Even if we solved that, even if we invented some miraculous preservation technique that suspended metabolism without killing the organism, you'd still face the radiation countdown. A frozen body is not shielded from cosmic rays. The DNA still gets hit. The mutations still accumulate. You'd wake up 70 years later riddled with cancers that developed while you were unconscious. And let's say you solved that too. Let's say you invented shielding and cryonics and fusion drives and navigation systems that somehow overcome every obstacle. You'd still face the final countdown, the one that matters most, the heat death of human ambition. Because here's the truth. No one wants to say out loud, "We're not going to do this." Not because we can't figure out the engineering, but because the timeline required exceeds the attention span of civilizations. A crude interstellar mission would take multiple human lifetimes to plan, build, launch, and complete. The people who greenlight the mission will be dead before the spacecraft leaves the solar system. The engineers who design it will be dead before it reaches the halfway point. The crew who launch will die en route. And the civilization that sent them may not even exist anymore by the time any signal returns. Human societies don't operate on century-long timelines. We struggle to maintain projects across decades. Political priorities shift. Funding evaporates. Interest wanes. The countdown to mission cancellation is measured not in physics, but in fiscal years and election cycles. And it always runs out before the spacecraft does. This is the quiet countdown no one talks about. The one where humanity, as a species, simply loses interest, where the initial excitement fades, the budgets get reallocated, and the mission becomes a historical footnote, a monument to ambition that exceeded our ability to care. And that's just for Proxima Centauri, 4 light-years, the closest star. If you want to reach anywhere interesting, a planet that might actually support life, a system with resources worth the journey, you're talking about tens or hundreds of light years, timelines that stretch into centuries or millennia, countdowns so long that the concept of human might not even mean the same thing by the time they expire. The solar system has a boundary. Not a wall, not a barrier you can see or touch, but a threshold defined by physics and the sun's influence. Cross it, and you enter interstellar space, a region where the sun's solar wind no longer dominates, where the magnetic field weakens to near zero, where the gravitational pull becomes so faint that other stars begin to assert their own influence. This boundary is called the heliopause, and it sits roughly 18 billion kilometers from the Sun, about 123 astronomical units, or AU, where 1 AU is the distance from Earth to the Sun. Voyager 1 crossed this boundary in 2012. Voyager 2 followed in 2018. These machines are now officially in interstellar space. They're the only human-made objects to ever leave the solar system, and they'll never come back. But here's what almost no one realizes. Voyager's crossing doesn't mean the solar system is small. It doesn't mean the boundary is nearby. It means we've barely scratched the surface of what escape actually requires. Because the heliopause is not the edge of the solar system, not even close. Beyond the heliopause lies the Oort Cloud, a vast, spherical shell of icy bodies that stretches from roughly 2,000 astronomical units to as far as 100,000 astronomical units from the Sun. That's nearly 2 light-years. These objects, comets, planetesimals, frozen remnants of the solar system's formation, are still gravitationally bound to the Sun. They still orbit it. They're still part of the system. And to truly escape the solar system, to break free of the Sun's gravitational influence entirely, you'd have to travel through the entire Oort Cloud and out the other side. At Voyager, one's current speed, about 17 kilometers per second, it will take roughly 300 years to reach the inner edge of the Oort Cloud, another 30,000 years to pass through it completely. 30,000 years. That's the countdown to true escape, and it's measured not in human lifetimes, but in epochs. Civilizations rise and fall in less time, languages evolve into unrecognizability, species go extinct. And Voyager 1 will still be drifting through a cloud of ice that technically belongs to our Sun. Now imagine a human crew trying to make that journey. They can't. The countdowns we discussed in the first part, radiation, bone loss, psychological collapse, are calibrated for journeys measured in decades. 70 years to Proxima Centauri is already beyond the limits of human survivability. 30,000 years to escape the Oort Cloud is not a human timescale. It's not even a historical timescale. It's geological. It's evolutionary. You could argue for generation ships, spacecraft large enough to support a breeding population that lives, reproduces, and dies over thousands of years, with the distant descendants of the original crew eventually reaching interstellar space. It's a theoretically possible concept, but the countdowns embedded in that scenario are even more insurmountable than a single lifetime mission. Start with population genetics. To maintain genetic diversity and avoid inbreeding depression over hundreds of generations, you'd need a minimum viable population of several hundred individuals. Some studies suggest 500, others say closer to 2,000. Each of those individuals requires life support, air, water, food, living space. A generation ship carrying 500 people would need to be enormous, comparable in size to a small city. The mass would be staggering. The energy required to accelerate it to even a fraction of interstellar speeds would exceed anything we could generate with current or near-future technology. Then there's the ecological countdown. A generation ship isn't just a spacecraft, it's a closed-loop ecosystem. Every atom of oxygen, every molecule of water, every calorie of food has to be recycled indefinitely. There's no resupply, no margin for error. If your water reclamation system fails, everyone dies of dehydration within days. If your algae farms get contaminated with a pathogen, your food supply collapses within months. If your atmospheric scrubbers degrade, carbon dioxide buildup kills the crew within weeks. We've never built a closed-loop life support system that functioned for more than a few years. Biosphere 2, the most ambitious attempt, lasted less than 2 years before external intervention was required. The ISS requires regular resupply missions, tons of water, food, and spare parts shipped up from Earth every few months. A generation ship wouldn't have that option. It would need to function perfectly, without external input, for 30,000 years. The countdown to ecological collapse in a closed system is measured in decades at best. Over centuries, small inefficiencies accumulate. Trace elements leach into unusable forms. Soil chemistry drifts. Microbial populations shift in unpredictable ways. And once the balance tips, it cascades. The system doesn't degrade slowly. It collapses suddenly. One generation is fine. The next is starving. Even if you solved the engineering, you'd face the biological countdown of genetic drift and mutation. Over hundreds of generations in an isolated population, random mutations accumulate. Some are harmless, some are beneficial, some are lethal. Without the buffering effect of a large, diverse gene pool, the kind that exists on Earth with billions of individuals, deleterious mutations can become fixed in the population through sheer chance. This is called genetic drift, and it's a countdown to population collapse through accumulated genetic load. Fruit fly populations in controlled environments show measurable fitness decline within 50 generations. Extend that to humans, and you're looking at serious problems within 1,000 years, well before the generation ship exits the Oort Cloud. Birth defects increase, immune systems weaken, fertility drops, and there's no way to import fresh genetic diversity when you're light years from the nearest other human. Then there's the cultural countdown. How do you preserve knowledge, purpose, and social cohesion over 1,000 generations? The original crew launched with a mission: reach interstellar space. But their children didn't choose that mission, neither did their grandchildren or great-great-great-grandchildren. By generation 50, the mission is ancient history. By generation 100, it's mythology. By generation 500, no one remembers why they're in the ship at all. Languages evolve. On Earth, languages become mutually unintelligible within 500 to 1,000 years. Latin became French, Spanish, Italian, Portuguese, Romanian, separate languages in that time frame. On a generation ship with no external cultural influence, linguistic drift would be even faster. By the time the ship reaches its destination, the crew might not be able to read the original mission logs or technical manuals. The knowledge base degrades, skills are lost, and without intervention, the society inside the ship devolves into something unrecognizable. There's a countdown to civilizational amnesia, and it runs faster than you'd think. Oral traditions corrupt within a few generations. Written records require literacy, archival systems, and a culture that values preservation. What happens when a generation rebels against the ship's authority? When they decide the mission is pointless and repurpose the vessel for something else? When infighting breaks out and knowledge is deliberately destroyed? History is full of examples. The Library of Alexandria burned. The Bronze Age collapsed. Civilizations with advanced knowledge, astronomy, mathematics, engineering vanished, leaving only ruins. And those were civilizations rooted on a planet with access to resources, new ideas, trade, immigration. A generation ship has none of that. It's a single thread of culture, unmoored, drifting through the void. The countdown to cultural collapse is measured in centuries, not millennia. And let's grant for the sake of argument, that you solve all of these problems. You build a generation ship with perfect life support, genetic diversity, and cultural continuity. You launch it toward the outer solar system with the goal of eventually reaching interstellar space. You've solved every biological and social countdown. You still can't escape the thermodynamic countdown. A generation ship requires power, constant, reliable power, for 30,000 years. You can't use solar panels. The farther you get from the sun, the weaker the sunlight. By the time you reach the Oort Cloud, solar irradiance is effectively zero. You can't use chemical batteries, they discharge over time, and no battery chemistry we know of maintains charge for millennia. You can't use fossil fuels, you'd need to carry an impossible amount. The only viable option is nuclear power. Fission reactors using uranium or thorium could theoretically provide power for decades, but they require fuel. And fuel is mass, and mass is something you have to accelerate. Worse, fission reactors have a countdown built into their physics: fuel depletion. Uranium-235 has a half-life of 700 million years, but in a reactor, you're burning it actively. A typical fission reactor consumes its fuel in a few years. Even a breeder reactor, which generates more fuel than it consumes by converting U-238 to plutonium, eventually runs out of feedstock. Fusion power might help, if we ever figure out how to build a functioning fusion reactor, which we haven't yet despite 70 years of research. But even fusion requires fuel: deuterium, tritium, helium-3. You'd have to carry enough for 30,000 years. The mass penalty is enormous, and all of this assumes the reactor itself doesn't break down. Reactors have mechanical components: pumps, heat exchangers, turbines, control rods. They wear out. They need maintenance, they need replacement parts. Over 30,000 years, you'd need to manufacture those parts on board, which means carrying raw materials, machine tools, technical expertise. You're not just building a spaceship, you're building a self-sustaining industrial civilization inside a can. The countdown to mechanical failure is relentless. Ball bearings wear down, seals crack, metal fatigues, radiation embrittles structural components, and in the vacuum of space, with no atmosphere to moderate temperature swings, materials expand and contract with every shift in solar exposure, accelerating wear. Every component has a mean time between failures, MTBF. For complex systems, the MTBF can be thousands of hours, which sounds like a lot until you're operating for 30,000 years. That's 262 million hours. If a critical system has an MTBF of 10,000 hours, it will fail 26,000 times over the course of the journey. You'd need 26,000 replacement parts, or the ability to manufacture them on board, or redundancy so extreme that the ship's mass becomes prohibitive. The countdown to irreparable failure is a statistical certainty, and when a critical system fails, reactor cooling, life support, navigation, and you can't fix it, the mission ends. Everyone dies. The ship becomes a tomb drifting through the dark. Let's zoom out. Let's say you accept that generation ships are impractical, that human biology can't endure the journey, that the timelines are too long. You pivot, you say, fine, we won't send living humans. We'll send frozen embryos. We'll send artificial wombs. We'll send robots programmed to raise the children when they arrive. It's called a seed ship. And it's been proposed seriously by researchers who recognize that adult humans are the weak link. But the countdowns don't go away. They just shift. Frozen embryos degrade over time. Cosmic radiation damages DNA, even in cryogenic storage. You'd need shielding, which adds mass. You'd need power to keep the cryogenic systems running, which adds fuel. You'd need the artificial wombs to function perfectly after 30,000 years in space, with no maintenance, no testing, no way to verify they still work until you try to use them. If the system fails, the embryos thaw and die, or they're born into a malfunctioning ship with no one to care for them. And let's say the embryos survive. Let's say the artificial wombs work. You've now got a generation of children born on a spacecraft, raised by robots, with no adult humans to teach them how to be human. How do they learn language, socialization, culture, ethics? You can program the robots with instructions, but robots can't replace parents. They can't provide the emotional bonding, the intuitive understanding, the adaptive responses that human development requires. Studies on institutionalized children raised in orphanages with minimal human contact show severe developmental deficits, language delays, attachment disorders, cognitive impairment. And those children at least had other children around them. The seed ship children would be raised in total isolation from organic human contact. The psychological countdown to developmental collapse starts at birth. Even if they survive, even if they grow into functional adults, they face the same countdowns as a generation ship: resource depletion, mechanical failure, cultural drift. Except now, they're starting from scratch with no inherited knowledge, no oral traditions, no collective memory of Earth. They're feral humans on a decaying spacecraft, and the countdown to mission failure is even shorter because they don't have the institutional knowledge to maintain the systems that keep them alive. Every scenario, every proposed solution, every clever workaround ends the same way. The countdowns win. Biology fails, machines fail, societies fail, and the solar system boundary remains uncrossed by living humans. But let's go even further. Let's assume some unimaginable breakthrough. Let's say we invent uploading, we digitize human consciousness, transfer it to a computer substrate, and send that into space. No biological body, no life support, no food, no air. no gravity. Just information stored in hardware running on minimal power. This is the transhumanist escape hatch. If we're not biological anymore, the biological countdowns don't apply. Radiation can't give us cancer. Zero gravity can't atrophy our muscles. We don't age. We don't die. We just exist as patterns of information experiencing something that might resemble consciousness sailing through the void on a chip that draws microwatts of power. It's seductive. It sounds like a solution, but it doesn't escape the solar system. It abandons humanity. Because here's the question no one wants to confront. If you upload your mind to a computer, is it still you? Or is it a copy? A simulation that thinks it's you but isn't? Philosophers call this the continuity of consciousness problem, and there's no agreed-upon answer. If your biological brain is destroyed in the uploading process, you, the subjective experiencer reading these words right now, die. The thing that wakes up in the computer is not you. It's a replica. It has your memories, your personality, your sense of identity, but the unbroken thread of subjective experience that makes you you has been severed. You can't test this. You can't verify it. Because if it's true, the original you never knows. You just die. And the copy goes on thinking it succeeded. And even if we grant that uploading somehow preserves the real you, you still face the hardware countdown. Computer chips degrade. Cosmic rays cause bit flips, random errors in memory that corrupt data. Over thousands of years, even with error-correcting code, the cumulative damage is fatal. Your mind, stored as data, slowly corrupts. Memories scramble. Thought processes malfunction. You don't die suddenly. You go insane gradually as the information that defines you decays bit by bit, and you can't repair it because you're traveling through interstellar space, light years from any support infrastructure, running on a chip that can't replace itself. The countdown to data corruption is as certain as the countdown to radiation damage in a biological body. The substrate changes. The outcome doesn't. This is the inescapable pattern. Every attempt to cross the solar system boundary runs into a wall built from countdowns. Physics countdowns, biology countdowns, engineering countdowns, social countdowns, thermodynamic countdowns. They overlap, they compound, and they all terminate in failure. And we haven't even addressed the most fundamental countdown of all, the one governed by the universe itself. The universe is expanding, not just expanding, but accelerating. Distant galaxies are moving away from us faster and faster, carried by the expansion of space itself. This expansion is driven by dark energy, and it's not slowing down. In fact, it's speeding up. Right now, the observable universe, the region of space from which light has had time to reach us, is about 93 billion light-years in diameter. But observable doesn't mean reachable. Because space is expanding, there's a boundary called the cosmic event horizon. Beyond this horizon, objects are receding from us faster than the speed of light. Not because they're moving through space, but because space itself is expanding. Light from those regions will never reach us, no matter how long we wait. And we can never reach them, no matter how fast we travel. The cosmic event horizon is currently about 16 billion light-years away, and it's shrinking. Every second more of the universe passes beyond our reach, accelerating away into the unreachable void. This is the ultimate countdown, the countdown to cosmic isolation. In about 100 billion years, the expansion of the universe will have carried every galaxy outside our local group beyond the cosmic event horizon. Future civilizations looking up at the sky will see nothing. No distant galaxies, no cosmic microwave background, no evidence that the universe extends beyond their local cluster. They'll be trapped in an island of stars, surrounded by infinite darkness, with no way to know that anything else ever existed. But humans won't be around to see that countdown expire, because long before the universe goes dark, our own galaxy, the Milky Way, faces a countdown of its own. In approximately 4.5 billion years, the Milky Way will collide with Andromeda, the nearest large galaxy. The two will merge into a single elliptical galaxy that astronomers have already nicknamed Milkomeda. This isn't a gentle process. Stars will be flung into new orbits. Some will be ejected from the galaxy entirely, cast into intergalactic space. Planets will be torn from their stars. Solar systems will be disrupted. And Earth, if it still exists, will be in the middle of it. Actually, Earth won't exist, because 1 billion years before the galactic collision, Earth will already be dead. The Sun is getting brighter, not quickly, but steadily. It's a consequence of stellar evolution. As the Sun fuses hydrogen into helium, the helium accumulates in the core, increasing the core's density and temperature. This makes the fusion reactions run hotter, which makes the Sun more luminous. Every billion years, the Sun's brightness increases by about 10%. Right now, Earth is in the habitable zone, the region around the Sun where liquid water can exist. But as the Sun brightens, the habitable zone moves outward. In about 1 billion years, Earth will be too close. The oceans will evaporate. The atmosphere will be stripped away by solar wind. The surface will become a scorched, lifeless desert, like Venus. Any humans still on Earth will have died long before that. The countdown to Earth's uninhabitability is measured in hundreds of millions of years, maybe less. And to escape it, humanity would need to leave not just Earth, but the entire solar system. We'd need to find a new star, a new planet, a new home. But as we've established, we can't do that. The countdowns that prevent us from leaving the solar system, the radiation, the distance, the time, the biology, are insurmountable. So when Earth becomes uninhabitable, humanity dies with it, unless we don't leave biologically, unless we build habitats, space stations, O'Neill cylinders, massive rotating structures that generate artificial gravity, support ecosystems, and drift through the solar system independent of planets. This is the fallback vision. Humanity as a spacefaring species, not planet-hopping between stars, but living permanently in constructed environments. It's more achievable than interstellar travel. It doesn't require faster-than-light drives or generation ships. It just requires engineering and resources, but it doesn't escape the solar system. It just delays the countdowns, because those habitats still depend on the Sun. They need energy, and the Sun provides it. They need raw materials and the asteroid belt. The moons, the planets provide them. But the Sun is dying. In 5 billion years, it will exhaust its hydrogen fuel and begin fusing helium. It will expand into a red giant swallowing Mercury, Venus, and possibly Earth. The habitable zone will move outward past Mars, past the asteroid belt, maybe as far as Jupiter's moons. Humanity could migrate outward with the habitable zone, building new habitats in the outer solar system as the inner system becomes uninhabitable. But it's a temporary reprieve. Because when the Sun exhausts its helium, it will shed its outer layers in a planetary nebula, leaving behind a white dwarf, a dense, cooling ember that provides almost no energy. The solar system will go dark and cold. and any habitats depending on solar energy will die. The countdown to the sun's death is 5 billion years. That sounds like a long time. It's longer than the entire history of complex life on Earth, but it's not infinite. It's a deadline, and unless humanity leaves the solar system, it's a deadline we can't escape. Except we can't leave. We've established that. So the countdown runs out, and humanity ends. This is the core of the cosmic trap. The boundaries that protect us are also the boundaries that doom us. The sun gives us energy, but it's dying. The solar system gives us resources, but it's finite. And the distances to other stars, the escape routes to new suns, new systems, are so vast that no human will ever cross them alive. We are trapped in a pocket of space and time, bounded by physics on all sides, riding a countdown that ends in extinction, and no amount of technology, ambition, or hope changes the math. There's a specific number that governs whether humanity ever leaves the solar system, and most people have never heard of it. It's called the Tsiolkovsky rocket equation, and it's not a guideline or an approximation. It's an iron law of physics that has constrained every spacecraft ever built and will constrain every spacecraft ever conceived. The equation itself is deceptively simple. Delta V equals VE times natural log of m0 over mf. Delta V is the change in velocity you can achieve. VE is the exhaust velocity of your rocket. m0 is the initial mass of the spacecraft, including fuel. mf is the final mass after all fuel is burned. The natural logarithm in the middle is what makes the equation brutal. What this equation tells you is that to go faster, you need more fuel. But more fuel means more mass, and more mass means you need even more fuel to accelerate that mass. It's an exponential trap, and it creates a countdown to physical impossibility that starts the moment you decide how fast you want to go. Let's run the numbers for an interstellar mission. You want to reach Proxima Centauri in a human lifetime, say 40 years. That's 4.24 light years divided by 40 years, which means you need to travel at about 10% the speed of light, 30,000 kilometers per second. We've already established that's 157 times faster than the Parker Solar Probe, the fastest human-made object ever. But let's see what the rocket equation says about achieving that speed. Assume you're using a fusion rocket, the most efficient propulsion system we can theoretically imagine that doesn't violate known physics. A fusion rocket might achieve an exhaust velocity of about 10,000 kilometers per second by fusing hydrogen into helium and directing the energy backward. That's optimistic, since we haven't built a functioning fusion reactor at all, let alone one that works in space. But we'll grant it. You need a delta V of 30,000 kilometers per second. Your exhaust velocity is 10,000 kilometers per second. Plug those numbers into the Tsiolkovsky equation and solve for the mass ratio. m0 over mf equals e to the power of 30,000 over 10,000 equals e to the power of 3, approximately equals 20. That means for every kilogram of final spacecraft mass, the crew compartment, the payload, the instruments, you need 20 kilograms of initial mass. In other words, 95% of your spacecraft is fuel, only 5% is everything else. Now, let's say your crew compartment, life support, shielding and supplies weigh 100 tons, a conservative estimate for keeping 6 people alive for 40 years. To achieve 10% light speed, you'd need to launch with 2,000 tons of fuel. That's already more massive than the International Space Station, and that's just to accelerate. You also need to decelerate at Proxima Centauri, or you'll fly past at 30,000 kilometers per second and never stop. Deceleration requires the same delta V, which means you need another 2,000 tons of fuel. But wait, you have to carry the deceleration fuel with you from the start. So now your initial mass is 100 tons payload plus 2,000 tons deceleration fuel plus x tons acceleration fuel, and x has to accelerate everything. Run the numbers again, and you find that x is approximately 42,000 tons. Your total spacecraft mass at launch is 44,000 tons, and only 100 tons of that is the actual mission payload. The rest is fuel. 44,000 tons is more than a fully loaded aircraft carrier, and that's using a fusion drive we don't have, with an efficiency we can't achieve for a mission profile that assumes perfect burns with no course corrections. Now add in the fuel you'd need to escape Earth's gravity well in the first place. Add in the fuel for mid-course corrections, because space is not empty, and you will need to dodge debris, adjust for gravitational perturbations, and correct navigation errors. Add in redundancy, because a fuel leak or engine malfunction 40 years from home means mission failure and crew death. The mass spirals upward, and every kilogram you add is a kilogram you have to lift from Earth's surface, which requires even more fuel. The countdown to impossibility is embedded in the mathematics. You can't engineer your way out of an exponential function. People propose alternatives. What about laser-pushed lightsails? What about nuclear pulse propulsion? What about antimatter rockets? Lightsails sound elegant. You build a massive, ultra-thin reflective sail, and you push it with a powerful laser beam from Earth orbit. The sail reflects the photons, and the momentum transfer accelerates the spacecraft. No on-board fuel required. In theory, you could accelerate indefinitely, limited only by the power of your laser. But here's the countdown problem. A light sail capable of carrying humans would need to be enormous, kilometers across, to have enough surface area to catch meaningful photon momentum while keeping the mass low. The sail material would need to be thinner than paper, yet strong enough to survive acceleration stresses and micrometeorite impacts. We don't have materials that meet those requirements. Worse, you can't steer a light sail once it's en route. The laser is back at Earth, and as the distance increases, the beam spreads. By the time the spacecraft is a light year away, the laser beam has diverged so much that almost none of it hits the sail. You lose propulsive efficiency with the inverse square of distance. The countdown to loss of thrust starts immediately and accelerates as you move away from the laser source. And you can't decelerate. The laser can only push you away from Earth. To slow down at your destination, you'd need a second laser already positioned at Proxima Centauri, aimed back at your sail, which obviously doesn't exist. So light sail missions are one-way, high-speed flybys. You scream past your target at 10% light speed, take a few snapshots, and keep going into the void forever. That's not a crewed mission, that's barely a probe. Nuclear pulse propulsion, the Orion drive concept, is conceptually simpler. You detonate nuclear bombs behind your spacecraft and ride the shockwave. Each explosion pushes you a little faster. It's brutally inefficient, insanely dangerous, and politically unacceptable. But the physics works. In the 1960s, NASA and the Department of Defense seriously studied it. The countdowns here are different but equally fatal. First, you need thousands of nuclear bombs. Each bomb adds mass, which means you need more bombs to accelerate that mass, which adds more mass. The rocket equation still applies. You've just replaced chemical fuel with fission bombs. Second, the shockwave from a nuclear explosion is not a gentle push. It's a violent, chaotic blast that subjects the spacecraft to extreme acceleration forces, tens or hundreds of Gs. Human bodies can't survive that. You'd need massive shock absorbers which add mass. You'd need structural reinforcement which adds mass. The mass penalty spirals, and you're back in the exponential trap. Third, detonating nuclear bombs in space violates the Outer Space Treaty, to which every spacefaring nation is a signatory. The political countdown to mission cancellation would expire before the first bomb was loaded onto the spacecraft. And fourth, the radiation from thousands of nuclear explosions would irradiate the crew compartment, the electronics, the structural materials. You'd need shielding so heavy that the spacecraft becomes unliftable. The countdown to radiation-induced failure starts with the first detonation and compounds with every subsequent blast. Antimatter rockets are the theoretical extreme, annihilate matter and antimatter, convert mass directly into energy via E = mc squared, and channel that energy into thrust. The energy density is unmatched, orders of magnitude better than fusion. In theory, an antimatter rocket could achieve exhaust velocities approaching a significant fraction of light speed, which would make the Tsiolkovsky equation much more forgiving. But the countdowns here are even more absurd. First, we don't have antimatter. We can produce it in particle accelerators, one atom at a time, at a cost of about $62.5 trillion per gram. To fuel an interstellar spacecraft, you'd need kilograms or tons of antimatter. The economic countdown to bankruptcy would expire before you'd accumulated a single gram. Second, we have no way to store antimatter. It annihilates instantly upon contact with normal matter, so you'd need a containment system that suspends it in a vacuum using magnetic fields, with zero tolerance for failure. A single power glitch, a single magnetic field fluctuation, and the antimatter touches the containment vessel and detonates with the force of a thermonuclear weapon. The countdown to catastrophic containment failure is measured in the meantime between failures of every component in the magnetic system, and over a 40-year journey, failure is certain. Third, even if you solved production and storage, the gamma radiation from matter-antimatter annihilation is so intense that it would require shielding so massive that, once again, the spacecraft becomes unliftable. The countdown to crew death from radiation exposure begins the moment the engine fires. Every propulsion system ever conceived runs into the same walls: mass, energy, radiation, time. The countdowns are inescapable because they're rooted in the fundamental laws of thermodynamics and relativity. You cannot cheat physics, you cannot negotiate with the rocket equation, and you cannot build a spacecraft that carries humans to another star system within a human lifetime. But there's an even deeper countdown at play, one that governs not just the engineering but the existential viability of the mission itself. It's the countdown to navigational error. Space is big. That's a cliche, but people don't grasp what it means in practice. When you aim a spacecraft at Proxima Centauri, a star 4.24 light-years away, you're aiming at a target that is moving, that you're moving relative to, and that will have moved by the time you arrive. Proxima Centauri orbits the galactic center at about 250 kilometers per second. Earth orbits the Sun at 30 kilometers per second. The Sun orbits the galaxy at 220 kilometers per second. Everything is in motion, and your navigation solution has to account for all of it over a 40-year flight time. A navigational error of just 1 degree at the spacecraft drift. Thrusters leak. Micrometeoroids impact the hull and impart tiny velocity changes. Solar radiation pressure nudges you off course. Gravitational perturbations from passing objects, rogue planets, brown dwarfs, interstellar gas clouds bend your path. You'd need constant course corrections, which means constant fuel expenditure, which eats into your delta V budget, which means you need to carry more fuel, which means more mass, and we're back to the rocket equation. The countdown to fuel exhaustion is accelerated by every correction you make, and you have to make corrections constantly or you miss the target. And here's the cruelest part. You can't see where you're going in real time. At 10% light speed, even light from your destination takes years to reach you. If you detect a navigational error at the halfway point, 20 years into the journey, it takes 20 years for your correction signal to reach Earth, if you're even sending one, and another 20 years for Earth's response to reach you. By then, you're already past the point where the information is useful. You're flying blind on a 40-year ballistic trajectory with no real-time feedback, no margin for error, and no way to abort if something goes wrong. The countdown to mission failure is ticking from the moment of launch, and the odds are overwhelmingly against success. Now, zoom out further. Let's say you solve every engineering problem. You invent fusion drives, antimatter containment, perfect navigation, and biological countermeasures for radiation and zero gravity. You launch a crewed mission to Proxima Centauri, and it succeeds. The crew arrives alive. They study the system. They send data back to Earth. That data takes 4.24 years to arrive, traveling at the speed of light. So the round-trip communication time is 8.5 years. If mission control on Earth sends a message, "How are you doing?" the response arrives nearly a decade later. If something goes wrong, a medical emergency, a system failure, a critical decision that requires expert input from Earth, there is no help coming. The countdown to irreversible consequence is built into the structure of space-time itself. This is called the light speed lag, and it's not a technological problem. It's a fundamental limit imposed by relativity. Information cannot travel faster than light, ever, period. No matter what technology you develop, you cannot send a message to Proxima Centauri and get a response in less than 8.5 years. Einstein's equations don't leave any loopholes. For a crewed mission, this means absolute isolation. The crew is on their own for the entire journey and the entire stay at the destination. If they need spare parts, medical supplies, or expertise that wasn't packed into the ship, they're out of luck. The countdown to unsolvable crisis is determined by the inventory of supplies and the skills of the crew, and both are finite. And if something catastrophic happens, if the crew dies, if the ship is destroyed, if the mission fails, Earth won't know for 4.24 years. By the time the lack of signal is noticed, the disaster is ancient history. There's no rescue, no recovery, just silence across the void. This is the reality of interstellar distance. It doesn't just separate you in space, it separates you in time. And time is a countdown that never stops. But let's push even further into the countdowns embedded in the mission architecture itself. Let's talk about the return journey. Most interstellar mission proposals are one way. The crew launches, travels for decades, arrives at the destination, and stays there until they die. There's no coming back. And the reason is simple. A round trip doubles the fuel requirement. If you need 44,000 tons of fuel to get to Proxima Centauri, you need another 44,000 tons to get back. But you have to carry the return fuel with you from Earth, which means your initial launch mass includes both the outbound and return fuel. Run the Tsiolkovsky equation again, and the numbers explode. You'd need hundreds of thousands of tons of fuel. It's not buildable. It's not launchable. It's not achievable with any propulsion system we can imagine. So the mission is one way. The crew accepts that they will never see Earth again. They will never feel Earth's gravity. They will never breathe Earth's air. They will die in a metal tube orbiting a foreign star or on a hostile planet or in the cold vacuum of space when life support fails. This creates a countdown to psychological collapse that's even more severe than a generation ship. Because on a generation ship, at least the distant descendants might imagine reaching a destination. On a one-way interstellar mission, you know you're going to die en route or at a destination you'll never truly call home. There's no hope of return. No possibility of rescue. No connection to the world you came from. The countdown to despair, to mission abandonment, to crew mutiny or suicide is compressed. Studies of isolated research stations show that morale collapses when personnel believe their situation is permanent and inescapable. Hope requires the possibility of change. Remove that possibility, and the human mind breaks. You could argue that the crew would volunteer knowing the mission is one way, that they'd be psychologically screened and trained for permanent isolation. Maybe. But training and screening can't change the fundamental wiring of the human brain. We evolved as social creatures embedded in dynamic environments. Permanent exile from every environment you evolved for, with no possibility of return, is not something humans are built to endure. The countdown to mental breakdown is not a technological problem. It's a biological one. And biology doesn't update with software patches. And here's another countdown no one talks about. The countdown to obsolescence. Let's say you launch a crewed mission to Proxima Centauri in the year 2050. The journey takes 40 years, so the crew arrives in 2090. But back on Earth, technology keeps advancing. In 2060, a breakthrough in propulsion allows spacecraft to reach 20% light speed. A new mission launches in 2070 and arrives at Proxima Centauri in 2091, 1 year after the original crew, but with a crew that only travelled for 21 years instead of 40. The original crew spent half their lives in transit and arrived older, more radiation damaged, more psychologically broken, only to be greeted by a newer mission that left decades after them and arrived with a younger, healthier crew using superior technology. This is called the weight calculation, and it's a countdown to mission irrelevance. If technology is improving fast enough, it's always better to wait and launch later with better tech. But if everyone waits, no one ever launches. The countdown to decision paralysis never expires, it just loops indefinitely. And it gets worse. If propulsion technology improves exponentially, the later you launch, the faster you arrive. Eventually, you reach a point where a mission launched centuries from now would arrive before a mission launched today. At that point, launching today is not just inefficient, it's pointless. This is the interstellar mission paradox. The best time to launch is always in the future, which means the optimal strategy is to never launch at all. The countdown to mission approval is infinite, and no one ever leaves. But buried beneath all of these countdowns, the engineering countdowns, the biological countdowns, the psychological and thermodynamic and navigational countdowns, is one final existential countdown that determines whether humanity ever becomes an interstellar species. It's the countdown to extinction. Earth is fragile. Civilization is fragile. Humanity's survival is not guaranteed. Asteroid impacts, supervolcanic eruptions, nuclear war, pandemics, climate collapse, any of these could end human civilization within centuries. And if civilization collapses before we've developed the technology to leave the solar system, we never get another chance. Because interstellar travel is not a primitive technology. It's not something you can build with iron and steam. It requires industrial capacity, energy abundance, computational power, material science, and international cooperation on a scale that only advanced civilizations can muster. If we collapse back to a pre-industrial state, we don't rebuild to the stars. We rebuild to subsistence agriculture, and we stay there. The countdown to civilizational collapse is unknown, but it's ticking. Every year we delay developing interstellar capability is a year closer to potential extinction. And if extinction comes before capability, the countdown ends permanently. Humanity never leaves the solar system because humanity no longer exists. This is the stakes no one wants to confront. We're in a race between technological advancement and existential catastrophe, and the finish line is leaving the solar system before something wipes us out. And right now, we're losing. The solar system is not just a physical boundary, it's a temporal boundary, a deadline written into the fabric of reality. And on the other side of that boundary is not freedom or expansion or a glorious interstellar future. It's just more void, stretching out forever, unreachable by human hands. There's a concept in physics called the Kármán line, the boundary at 100 kilometers above Earth's surface, where aeronautics ends and astronautics begins. Cross it, and you're officially in space. It's arbitrary, a human-defined threshold, but it serves a purpose. It marks the point where the rules change, where the atmosphere is too thin to support flight, where you're no longer part of Earth's protective envelope. The solar system has a similar boundary, except it's not arbitrary and it's not defined by international agreement. It's defined by the point where the sun's influence fades to insignificance, where you transition from near the sun to between the stars. We've already discussed the heliopause, where solar wind pressure balances with interstellar medium pressure, and the Oort Cloud, which extends the sun's gravitational dominance out to nearly 2 light years. But there's another boundary, less discussed, but equally significant, the gravitational sphere of influence. It's the distance at which the sun's gravity becomes weaker than the gravity of the next nearest star. For the sun, that boundary sits at approximately 1.5 light years, halfway to Proxima Centauri. This creates a countdown to gravitational transition. If you launch a spacecraft from Earth and accelerate it to escape velocity fast enough to break free of the sun's gravity entirely, it will still take tens of thousands of years to reach this boundary. Voyager 1, currently the most distant human-made object, is traveling at 17 kilometers per second relative to the Sun. At that speed, it will take roughly 80,000 years to travel 1.5 light years. 80,000 years. That's not a human timescale. That's not a civilizational timescale. That's longer than anatomically modern humans have existed as a species. And Voyager is unmanned, unshielded, and requires no life support. A crewed mission would be slower, heavier, and vastly more complex, pushing the timeline to hundreds of thousands of years. The countdown to true solar system escape, measured by gravitational influence, is so long that it ceases to have meaning in human terms. You don't plan for timelines like that. You don't build missions around them. You just acknowledge that the boundary exists and that no human will ever cross it alive. But let's interrogate the countdowns even more carefully. Let's talk about what happens to the human body not over decades, but over the full span of an interstellar journey measured in centuries or millennia. Because if generation ships are the only theoretical path forward, we need to understand what hundreds of generations in space does to human biology. Evolution doesn't stop. It's not something you can pause or opt out of. Every generation, random mutations occur. In a large, diverse population on Earth, most deleterious mutations are filtered out by natural selection. Individuals carrying harmful genes are less likely to survive and reproduce, so the genes don't spread. But in a small, isolated population like a generation ship, the dynamics change. With only a few hundred or few thousand individuals, random genetic drift dominates. Harmful mutations can become fixed in the population purely by chance, especially if the mutation is recessive or has subtle effects that don't kill immediately. Over hundreds of generations, the genetic load accumulates, fertility drops, infant mortality rises, heritable diseases become endemic. Studies of isolated populations on Earth, island communities, remote villages, religious sects, show this pattern consistently. Genetic bottlenecks lead to increased rates of hereditary disorders. The Amish, the Ashkenazi Jews, isolated Polynesian islands, all show elevated frequencies of specific genetic diseases because their populations were small and isolated for extended periods. Now, take that effect and extend it over 1,000 generations in a sealed spacecraft with zero possibility of gene flow from outside populations. The countdown to genetic collapse is measured in centuries, and the outcome is inevitable. Increasing rates of birth defects, declining average health, and eventual extinction as the population becomes unable to reproduce viable offspring. You could mitigate this with genetic engineering, actively editing embryos to remove deleterious mutations, maintaining genetic diversity through stored DNA, implementing breeding programs to maximize heterozygosity. But this requires technology, infrastructure, and a level of social control that may not be sustainable over millennia. And it raises profound ethical questions. Who decides which genes are good and which are bad? Who enforces reproductive restrictions? What happens when the population rebels against genetic management? The countdown to loss of genetic management capability runs parallel to the countdown to genetic collapse. If the technology fails, if the expertise is lost, if the political will to enforce eugenics evaporates, the natural drift resumes and the population dies out. And even if you maintain perfect genetic health, you face another biological countdown: adaptation to the spacecraft environment. Humans evolved on Earth. Our bones, muscles, cardiovascular system, immune system, every aspect of our physiology is calibrated for Earth's gravity, atmosphere, microbial environment, and circadian rhythms. Live for hundreds of generations in a different environment, and evolution will adapt you to that environment. In microgravity, individuals with naturally weaker bones might survive just fine. There's no evolutionary pressure for strong bones if you never experience load-bearing stress. Over generations, the genetic variants that promote bone density would be lost. The same applies to muscle mass, cardiovascular strength, immune function. The population would evolve to be optimized for the spacecraft environment. Lighter bones, weaker muscles, immune systems that no longer need to fight off Earth's pathogens. This creates a one-way countdown to physiological incompatibility. After 1,000 generations in space, the population would no longer be able to survive on Earth, or on any planetary surface with significant gravity. They'd be space-adapted humans, incapable of returning to the environment their ancestors left. In science fiction, this is often portrayed as a triumphant evolutionary leap, humans transcending their planetary origins. In reality, it's a trap, because if your destination is a planet and you've evolved in zero gravity for a millennium, you can't land, you can't colonize, you can't walk on the surface. You're stuck in orbit, dependent on the spacecraft that carried you, and the mission, if it ever had a purpose beyond mere survival, has failed. The countdown to evolutionary divergence starts the moment you leave Earth, and it's irreversible without constant artificial selection to maintain Earth compatibility. And maintaining that compatibility requires subjecting every generation to artificial gravity, rigorous exercise, controlled breeding, essentially torturing them to prevent adaptation. Over centuries, that becomes unsustainable. So you face a choice: evolve and become incompatible with planets, or resist evolution and suffer the genetic and physiological consequences of maintaining an Earth-adapted genome in a non-Earth environment. Either way, the countdown ends in mission failure. Now, let's talk about energy in a way we haven't yet. The sheer thermodynamic impossibility of sustaining a closed-loop ecosystem for geological timescales. A generation ship is, by definition, a closed system. Energy comes in from the engines or solar panels. Waste heat radiates out into space. But matter, every atom of carbon, nitrogen, oxygen, hydrogen, has to be recycled indefinitely. There's no resupply, no import of fresh material. What you launch with is all you'll ever have. On Earth, ecosystems are sustained by an open flow of energy from the sun, and the biosphere is large enough that inefficiencies don't matter. A tree drops leaves, they decompose, nutrients return to the soil, new trees grow. The cycle isn't perfect, but the system is so massive that small losses are negligible. On a generation ship, the system is tiny. Every atom matters. If your water reclamation system is 99.9% efficient, you lose 0.1% of your water every cycle. That sounds trivial, but over thousands of cycles, it adds up. After 10,000 cycles, maybe 30 years of operation, you've lost 63% of your water to inefficiency and leakage. It's locked up in unusable chemical forms, absorbed into materials, or escaped as vapor into space. The same applies to every element essential for life. Carbon gets locked into non-biodegradable polymers. Nitrogen escapes as gas through micro-leaks. Phosphorus binds into insoluble minerals. The countdown to resource exhaustion is determined by the efficiency of your recycling systems, and no recycling system is 100% efficient. Thermodynamics forbids it. You could carry extra reserves, tanks of water, stockpiles of nutrients, buffers to account for losses, but reserves are mass, and mass is fuel, and we're back to the rocket equation. The more reserves you carry, the heavier the ship, the more fuel you need, the more impossible the mission becomes. The countdown to ecological collapse through gradual resource depletion is measured in decades or centuries, depending on efficiency. And when critical resources run out, the ecosystem crashes, crops fail, water runs out, the atmosphere becomes unbreathable, and everyone dies. Even if you achieve near-perfect recycling, you still face the entropy problem. The second law of thermodynamics states that in any closed system, entropy, disorder, always increases. You can locally decrease entropy by expending energy, but the overall trend is toward maximum disorder. In practical terms, this means that over time, your carefully organized systems degrade into chaos. Filters clog, pipes corrode, seals fail, microbes evolve in unexpected ways, Chemical reactions produce unwanted byproducts. The ship doesn't maintain itself, it decays, and fighting that decay requires constant energy input and maintenance. The countdown to entropic collapse is thermodynamically guaranteed. Over centuries, the cumulative disorder overwhelms your ability to maintain order. Systems fail faster than you can repair them. The ship becomes a drifting hulk of malfunctioning subsystems, and the crew, if they're still alive, can't keep up. This is not a solvable engineering problem. This is physics. The universe tends toward disorder, and you cannot stop it. You can only delay it. And on the time scales required for interstellar travel, the delay is insufficient. Now, let's address a question that often gets raised as a potential loophole. What if we don't send humans at all? What if we send human DNA, frozen embryos, or even just the information to reconstruct humans? A digital blueprint, transmitted as radio waves to a receiver at the destination, where machines build bodies and implant consciousnesses. These are variations on the same theme, sending the pattern of humanity rather than living humans. And while they avoid many of the biological countdowns, they introduce new ones that are equally fatal. Start with frozen DNA. You could, in theory, store genetic material in a radiation-shielded vault, keep it cryogenically frozen, and transport it across light years. At the destination, automated systems could grow humans from the DNA using artificial wombs. It sounds feasible, but DNA degrades over time, even when frozen. Cosmic radiation penetrates shielding and causes double-strand breaks. Background radioactivity from the spacecraft's materials, unavoidable trace isotopes in metals and electronics, slowly damages the genetic material. The countdown to DNA degradation is measured in thousands of years, maybe tens of thousands with perfect shielding. But for a journey spanning hundreds of thousands of years, the DNA would be too damaged to produce viable organisms by the time it arrived. You could carry multiple redundant copies, use error-correcting codes in the storage medium, or periodically repair the DNA using automated systems, but each of these solutions adds complexity, mass, and points of failure. And if the repair systems fail, and over hundreds of millennia they will fail, the DNA degrades beyond recovery. Okay, so skip the biological material entirely. Send digital information, the complete human genome, sequenced and encoded as data, transmitted as a radio signal to a receiver at the destination. The signal travels at the speed of light, arrives in 4.24 years, and machines at the destination decode the genome and synthesize humans from raw materials. Except there's no receiver at the destination, there are no machines, there's no infrastructure. Proxima Centauri is a star with planets, but those planets are not equipped with human-building factories waiting for our signal. You'd need to send the machines first, which means sending a physical spacecraft, which brings us back to all the previous countdowns. And even if you sent machines ahead, self-replicating robots programmed to build infrastructure on Proxima Centauri's planets, you're now dependent on those machines functioning flawlessly for thousands of years without maintenance, without supervision, without unexpected failures. The countdown to robotic system failure is governed by the same thermodynamic and mechanical laws as crewed spacecraft. Machines break, software corrupts, entropy wins. The only scenario where transmitting information works is if an advanced civilization already exists at the destination, capable of receiving and interpreting the signal and willing to reconstruct humans from the blueprint. But that's not interstellar travel. Interstellar. That's sending a message in a bottle and hoping someone finds it, and hoping they care. What about uploading human consciousness to machines and sending the machines? We touched on this earlier, but let's go deeper into the countdowns embedded in that scenario. Assuming you solve the philosophical problem of whether an upload is really you still face the hardware degradation countdown. Digital storage media degrades over time. Magnetic storage loses coherence. Flash memory experiences charge leakage. Even the most robust storage technologies have finite lifespans measured in decades, not millennia. Cosmic rays cause bit flips, random errors in memory where a 0 becomes a 1 or vice versa. Error-correcting codes can detect and fix some of these errors, but not all of them. Over thousands of years, the cumulative bit errors corrupt the data beyond recovery. The uploaded consciousness, your memories, your personality, your sense of self, slowly scrambles into nonsense. You could design redundant storage with multiple copies of the consciousness distributed across different memory modules. If one copy corrupts, the system reverts to a clean copy. But redundancy adds mass and power requirements, and eventually all copies accumulate errors. The countdown to data corruption is slowed but not stopped. And then there's the power countdown. A computer running a consciousness simulation requires power, constant, uninterrupted power for the entire journey. Where does that power come from? Solar panels are useless beyond the inner solar system. Batteries discharge, fuel cells run out of fuel. The only long-term option is nuclear, either fission or radioisotope thermoelectric generators, RTGs. RTGs use the decay of radioactive isotopes to generate heat, which is converted to electricity. Voyager 1 and 2 both use RTGs, and they've been running for over 40 years. But RTG power output degrades over time as the isotopes decay. Plutonium-238, the most common RTG fuel, has a half-life of 88 years. After 88 years, your power output is half the original. After 176 years, it's a quarter. After 350 years, it's 1/16. For a journey spanning thousands of years, you'd need either an enormous initial power supply, massive RTGs with tons of plutonium, or a fission reactor that generates power actively. Both add mass, both have failure modes, and both run out eventually. When the power dies, the simulation stops. The consciousness, if it's still coherent, simply ceases to exist. There's no backup generator in interstellar space, no cosmic AAA to jumpstart your battery. The countdown to power failure is as certain as the decay of radioactive isotopes, and when it expires, the mission ends in digital death. So every version of send something other than living humans runs into the same countdowns: degradation, entropy, power, and failure. The substrates change, but the outcomes don't. Let's return to the physical journey itself and examine a countdown we've mentioned but not fully explored: the collision countdown. Space is not empty. Even interstellar space, the void between stars, contains roughly 1 hydrogen atom per cubic centimetre. That sounds negligible, but at 10% the speed of light, each hydrogen atom you collide with hits your spacecraft with the kinetic energy of a high-velocity bullet. The kinetic energy of a particle is 1/2 mv squared, where m is mass and v is velocity. A hydrogen atom has a mass of about 1.67 times 10 to the minus 27 kilograms. At 30,000 kilometers per second, 10% light speed, each atom hits with about 7.5 times 10 to the minus 16 joules of energy. That sounds tiny, but you're colliding with billions of atoms per second. Over years, this cumulative bombardment erodes the spacecraft's hull. It's called spallation, High-energy particles slam into the surface, knock atoms loose and gradually wear away the material. The countdown to hull breach is determined by the thickness of your shielding and the density of the interstellar medium. Worse, the high-energy collisions produce secondary radiation, gamma rays, X-rays, neutrons that penetrate the hull and irradiate the interior. Even if the hull doesn't breach, the crew is exposed to radiation generated by the ship's own forward motion through space. The faster you go, the worse the radiation environment becomes. This creates a speed limit that has nothing to do with propulsion. Go too fast, and the interstellar medium becomes a lethal radiation source. The countdown to radiation death is accelerated by velocity, and there's no shielding thick enough to stop it without making the spacecraft too heavy to move. And hydrogen atoms are the best-case scenario. They're too small, too dark, too distant. Even if you could detect them, you couldn't maneuver to avoid them. Spacecraft don't handle like cars. Changing course requires fuel, time, and acceleration forces. By the time you see the grain, it's already hit you. The collision countdown is invisible, random, and unavoidable. And when it expires, the mission ends in explosive decompression or catastrophic structural failure. Now, consider the psychological countdown from a different angle, the countdown to loss of purpose. Imagine you're born on a generation ship. You didn't choose this life. You didn't volunteer for the mission. Your great-great-great-grandparents launched from Earth. But Earth is just a word to you, a mythical place in the ship's archives, as distant and abstract as Atlantis. You've never seen a horizon, never felt wind, never met anyone who isn't descended from the original 500 crew members. Your entire existence is maintaining systems you don't fully understand for a destination you'll never reach, in service of a mission that was decided by people who died centuries ago. What's your purpose? What's your motivation? Why should you care? This is the countdown to motivational collapse. On Earth, even in the hardest circumstances, purpose is derived from immediate goals: survival, family, community, achievement. But on a generation ship, the only goal is keep the ship running so future generations can continue the mission. That's abstract. It's distant. It requires sacrificing your own well-being for people who don't exist yet. How many generations can that last? 10, 20, 50? At some point, a generation says no. They reject the mission, they repurpose the ship, they abandon the goal. And the countdown to mission termination expires not because of engineering failure, but because the humans simply stopped caring. You could try to encode purpose into culture, religious doctrine, civic mythology, educational indoctrination. But cultures evolve, religions schism, myths are reinterpreted. Over centuries, the original mission becomes distorted beyond recognition. The ship becomes not a vehicle for interstellar travel, but a self-contained world where the journey is the only reality, and at that point the mission has already failed even if the ship is still moving. Because the goal is no longer to reach a destination, the goal is just to survive. And survival is not exploration, it's stagnation. There's a moment in every conversation about interstellar travel where someone invokes a phrase meant to end the discussion: we'll figure it out. As if human ingenuity is infinite, as if every problem is solvable given enough time, funding, and determination. As if the laws of physics are negotiable. But the countdowns we've examined are not engineering challenges waiting for clever solutions. They are fundamental limits imposed by the structure of reality itself. And the most important countdown of all, the one that determines whether humanity ever escapes the solar system, is the countdown to accepting this truth. Right now, we're in the denial phase. We tell ourselves stories about generation ships, fusion drives, suspended animation, and uploaded consciousness. We point to past achievements, landing on the moon, sending probes to the edge of the solar system as evidence that nothing is impossible. We cite Clarke's first law. When a distinguished but elderly scientist states that something is possible, he is almost certainly right. When he states that something is impossible, he is very probably wrong. But Clarke's law has limits. It applies to technological barriers, not physical ones. No amount of ingenuity will let you build a perpetual motion machine, travel faster than light, or reverse entropy. These aren't engineering problems, they're contradictions with the laws of thermodynamics and relativity. And the barriers to interstellar human travel fall into this category. The countdown to societal acceptance of this reality is unknown, but it's ticking. Every year, we invest billions in space agencies, private launch companies, and Mars colonization plans. We're operating under the assumption that humanity's future is among the stars. But that assumption rests on ignoring the countdowns, and ignoring them doesn't make them stop. Let's be precise about what we're claiming is impossible. We're not saying humans will never visit Mars. That's achievable with current technology and enough political will. We're not saying humans will never establish permanent settlements on the moon or in orbital habitats. Those are difficult but feasible. We're not even saying humans will never reach the outer solar system. A crewed mission to Jupiter or Saturn is theoretically possible, though extraordinarily expensive and dangerous. What we're saying is that no human will ever leave the solar system and arrive at another star system alive. Not in 100 years, not in 1,000, not ever. And the reason is that the countdowns, biological, physical, thermodynamic, psychological, all terminate before the journey ends. The distance to Proxima Centauri is 4.24 light-years, or 40 trillion kilometers. At the speed of the Voyager 1, the fastest human-made object to leave the solar system, the journey would take 73,000 years. No human lives that long. No generation ship maintains cohesion that long. No machine functions that long without maintenance from a supporting industrial base. To reduce the travel time to something within a human lifespan, you'd need to travel at a significant fraction of light speed, say 10 to 20%. But achieving those velocities with a crewed spacecraft requires energy expenditures and fuel masses that are physically unachievable. The rocket equation creates an exponential wall. The faster you want to go, the more fuel you need, but the more fuel you carry, the heavier you are, so you need even more fuel. The equation has no escape clause. You could propose exotic propulsion systems, antimatter drives, Bussard ramjets, laser-pushed lightsails. But antimatter requires production and containment technologies we don't possess, and may never possess. Bussard ramjets rely on scooping hydrogen from interstellar space and fusing it, but the densities are too low, and the engineering is beyond anything we can currently imagine. Lightsails can't decelerate and can't carry humans with meaningful shielding. Every theoretical propulsion system runs into a wall. Either it can't accelerate a crewed spacecraft to the necessary speeds, or it requires technologies so far beyond our current capabilities that invoking them is indistinguishable from invoking magic. And even if you solved propulsion, you'd still face the biological countdowns. Cosmic radiation doses over decades-long journeys cause cancer, cognitive decline, and cellular damage at rates that no amount of shielding can reduce to safe levels without prohibitive mass penalties. Zero gravity causes bone loss, muscle atrophy, and cardiovascular degradation that no exercise regimen can fully prevent. The human body is not designed for deep space, and you cannot redesign it without ceasing to be human. You could genetically engineer radiation-resistant humans or humans optimized for microgravity. But then you're not sending humans, you're sending post-humans, modified organisms that share our DNA but not our physiology. And those post-humans would face their own countdowns, evolutionary drift, genetic load accumulation, and incompatibility with planetary environments. The psychological countdowns are equally insurmountable. Decades of isolation in a confined environment, with no possibility of escape or rescue, will break most human minds. The research on isolation, submarine crews, Antarctic stations, sensory deprivation studies is unequivocal. Humans need variety, novelty, social complexity, and the possibility of change. Remove those, and mental health collapses. You could select for psychological resilience, train for extreme isolation, and provide virtual environments to simulate variety. But over decades, training fades, simulations become stale, and the reality of permanent confinement erodes even the most resilient psyches. The countdown to crew breakdown is not a question of if, but when. And when the crew breaks, when someone becomes violent, catatonic, or suicidal, there's no intervention team, no psychiatric hospital, no option to evacuate the individual. The mission continues with a broken crew, and the odds of success plummet. So when we say no human will ever escape the solar system, we're not being pessimistic, we're being precise. The countdowns are real, they're rooted in physics and biology, and they all expire before a human reaches another star. But there's a deeper question lurking beneath this conclusion. Does it matter? Does it matter if humans never leave the solar system as long as humanity survives? Does it matter if our descendants become something other than human, post-biological, uploaded, genetically modified beyond recognition, as long as something traceable to us continues? These are not scientific questions. They're philosophical ones, and they force us to confront what we mean when we talk about humanity's future in space. If the goal is simply to spread Earth-originating intelligence to other star systems, then biological humans are unnecessary. Send robots. Send AI. Send self-replicating probes programmed to explore, gather data, and transmit findings back to Earth. These missions face their own countdowns: data corruption, hardware failure, power depletion. But they're more survivable than crewed missions because machines don't need life support, don't suffer psychological collapse, and can be designed to operate for centuries with minimal maintenance. In fact, this is already happening. Voyager 1 and 2 are exploring interstellar space. New horizons will eventually leave the solar system. Future probes, potentially equipped with better propulsion, better power systems, better instruments, will push even farther. And they'll send back data that expands our understanding of the galaxy. But these probes are not us. They don't experience the universe. They don't have subjective consciousness. They don't wonder or dream or despair. They're tools, extensions of human curiosity, but not carriers of human experience. If what we want is for humans, conscious, subjective, living humans, to stand on the surface of a planet orbiting another star, to look up at an alien sky, to experience the visceral reality of being somewhere other than the solar system, then we're out of luck. The countdowns don't permit it. And maybe that's okay. Maybe the solar system is enough. The solar system contains 8 planets, hundreds of moons, millions of asteroids, billions of comets, and a vast expanse of space spanning 100,000 astronomical units if you count the Oort Cloud. That's an enormous volume to explore, exploit, and inhabit. Humans could build habitats in orbit around every major body, mine asteroids for resources, terraform Mars, establish colonies on the moons of Jupiter and Saturn, and still have barely scratched the surface of what's available. If the goal is survival, ensuring that humanity doesn't go extinct with Earth, then spreading throughout the solar system achieves that. A disaster on Earth wouldn't wipe out colonies on Mars, Europa, Titan, or orbital habitats scattered throughout the asteroid belt. The species survives, even if the homeworld doesn't. If the goal is expansion, growing in population, knowledge, and capability, then the solar system provides enough space and resources for billions or trillions of humans living in rotating habitats that generate artificial gravity and support closed-loop ecosystems. The energy from the sun can power all of it for billions of years. If the goal is exploration, learning about the universe, studying other worlds, answering fundamental questions about life and existence, then the solar system offers countless mysteries. We've barely explored it. We've landed humans on one other body, the moon. We've sent probes to a handful of planets and moons. We know almost nothing about the outer solar system, the Kuiper belt, the Oort cloud. There's a lifetime of discovery here, without ever needing to leave. But if the goal is transcendence, breaking free of our cosmic cradle, proving that life can escape its origins and spread across the galaxy, achieving some symbolic victory over the void, then we fail. The countdowns are too many, too overlapping, and too rooted in fundamental physical laws to overcome. And this is where the existential weight of the topic lands. Because the dream of interstellar travel is not really about propulsion or shielding or life support. It's about meaning. It's about refusing to accept that we're confined to a single star system, that our existence is bounded by the sun's influence, that the distances between stars are not just vast but existentially insurmountable. The dream is about immortality, not personal immortality, but species immortality. The idea that humanity will persist across the galaxy, seeding worlds, building civilizations, becoming something greater than what we are now. And the realization that we can't do this, that the countdowns prevent it, feels like a death sentence. But maybe it's not. Maybe it's a liberation. Because the dream of interstellar expansion comes with a cost. It defers purpose to the future. It says that what we do here now in the solar system is just preparation for the real work of spreading to the stars. It devalues the present in service of an unattainable future. If we accept that humans will never leave the solar system, we have to find meaning here. We have to build civilizations in the solar system that are worth living in, not just launching pads for missions that will never succeed. We have to treat the solar system not as a cage, but as a home, vast, diverse, and sufficient. This doesn't mean giving up on space exploration, it means recalibrating our goals. Instead of asking, how do we reach other stars, we ask, how do we thrive in the solar system for millions of years? Instead of building generation ships, we build sustainable orbital habitats. Instead of funding crewed missions to Proxima Centauri, we fund robotic probes that can gather data and transmit it back across light years. The countdowns that prevent interstellar human travel don't prevent this. They don't prevent us from becoming a multi-planetary species. They don't prevent us from spreading throughout the solar system. They don't prevent us from surviving for eons, building extraordinary civilizations and achieving things we can't currently imagine. They just prevent us from leaving. And there's a strange comfort in that, because it means we don't have to keep chasing an impossible dream. We don't have to sacrifice the present for a future that will never arrive. We can focus on what's achievable, exploring the solar system, establishing permanent settlements, developing technologies that let us live comfortably in space, and ensuring that humanity survives long enough to see the sun die billions of years from now. The solar system is not a prison. It's a vast, ancient, resource-rich region of space that we've barely begun to explore. The Oort Cloud alone extends nearly 2 light-years from the Sun. That's a sphere of space with a volume so large that the entire inner solar system, everything out to Neptune, is a rounding error by comparison. If we spent the next million years exploring just the Oort Cloud, we'd still find new objects, new mysteries, new frontiers. We don't need other stars to have an endless frontier. We have one right here. But the countdowns don't stop just because we reframe our goals. The sun is still dying. Earth will still become uninhabitable in 1 billion years. The Milky Way will still collide with Andromeda in 4.5 billion years. And in 5 billion years, the sun will expand into a red giant and vaporize everything in the inner solar system. These are the ultimate countdowns, cosmological timescales that dwarf everything we've discussed, and they raise the final question. If humanity can't leave the solar system and the solar system is doomed, does humanity have a future at all? The answer depends on what you mean by humanity. If you define humanity strictly as biological Homo sapiens living in the solar system, then no, we don't have a future beyond a few billion years. The sun's death is a hard deadline, and without the ability to leave, we're trapped. But if you define humanity more broadly as the information, culture, knowledge, and legacy we create, then the future is different. Because while humans can't leave the solar system, information can. We can send signals, radio transmissions, laser pulses, encoded data streams into the galaxy. These signals travel at the speed of light and they carry information about who we are, what we discovered, what we created. If another civilization exists out there, they might receive our signals and learn about us. We'd live on, not as organisms, but as data. This is what the Pioneer plaques and Voyager golden records were designed to do, serve as messages from humanity to the cosmos, carrying our image, our sounds, our coordinates. They're traveling away from the sun right now, and they'll continue for millions or billions of years, long after humanity is extinct. It's not the same as escaping, it's not the triumphant colonization of the galaxy, but it's a form of persistence, a way of saying, we were here, and this is what we were. And maybe that's all we can hope for, because the countdowns are relentless. The radiation countdown, the gravity countdown, the psychological countdown, the fuel countdown, the collision countdown, the thermodynamic countdown, the genetic countdown, the cultural countdown, the power countdown, the sun's death countdown. They overlap, they compound, and they all point to the same conclusion. Humans will never escape the solar system alive, not because we lack ambition, not because we haven't tried hard enough, but because the universe is structured in a way that makes it impossible. The distances are too vast. The energies required are too extreme. The biology is too fragile. The timelines are too long. We are creatures of Earth, shaped by Earth's gravity, warmed by Earth's sun, protected by Earth's magnetosphere. Leave that envelope and the countdowns begin. Travel far enough and they expire. And when they do, the mission ends, the crew dies, and the dream of interstellar humanity dies with them. This is not a tragedy, it's just a fact. A constraint imposed by physics, no different from the speed of light or the arrow of time. We cannot travel faster than light. We cannot reverse entropy, and we cannot send living humans to another star. The solar system is our boundary, not a political boundary, not a technological boundary, but a physical one, written into the equations that govern mass, energy, distance, and time. And on the other side of that boundary is not freedom, but death. So the countdown that matters most is not the countdown to when we leave. It's the countdown to when we accept that we won't. When we stop designing generation ships and start designing sustainable solar system civilizations. When we stop dreaming of exoplanets and start appreciating the worlds we already have access to. When we stop treating the solar system as a cage and start treating it as a home. That countdown is still running. And until it expires, we'll keep chasing an impossible dream, deferring meaning to an unreachable future, and ignoring the vast, beautiful, deadly, awe-inspiring frontier that's already within our grasp. The solar system is enough. It has to be, because it's all we'll ever have, and the clock is ticking. On Earth's habitability, 1 billion years until the oceans boil. On the sun's hydrogen fuel, 5 billion years until red giant expansion. On the Milky Way's collision with Andromeda, 4.5 billion years until galactic disruption. On humanity's window to establish a solar system-wide civilization, unknown but shrinking every year we delay. These are the real countdowns. Not the countdowns to leaving, but the countdowns to thriving, surviving, and making something meaningful in the time we have, in the place we're confined to. The solar system boundary is not a challenge to overcome, it's a fact to accept. And acceptance is not defeat, it's clarity. The clarity to focus on what's possible instead of what's not. The clarity to build for the long-term survival of humanity in the solar system, rather than the impossible dream of escape. Because in the end, there is no escape. There's only the time we have, the space we occupy, and the choices we make within those limits. The countdown has been running since the moment the first human looked up at the stars and wondered what lay beyond. And it will keep running until the last human looks up and accepts that some questions have answers we don't want to hear. No human will ever escape the solar system, not because we failed to dream big enough, but because the universe dreams bigger than we do in distances we can't cross, timelines we can't survive, and laws we can't break. The boundary holds. The countdowns expire, and humanity remains, for all of its existence, a species of one star.